All right, thanks, Joe. And thanks for the invitation to share some of the work that we've been doing, I guess now over the last 10 to 15 years. A lot of the data I'm going to show here is a result of two master's theses and undergrad we had work in the lab doing a lot of this separation work. And we're going to try and think about, we all use bulk sediment magnetic properties, but what are they and what do they tell us about the sediments that we're using to interrogate them with? So when we think about marine sedimentation, I'm going to focus on marine sedimentation in this talk. This is a combination of a bunch of different processes that result in the delivery of materials to the bottom of the sea. So we have influx of river sediments, we have the influence of ice margins, we have direct fallout from ashes. These get transported into the bottom of the ocean, they get moved around by different processes. So what we're looking at is this kind of like aggregation and agglomeration of all these different processes being focused and collecting at the bottom of the ocean. And we can collect ocean sediment cores that document some of these changes through time. And since the recognition, or the early recognition, 1996 was a long time ago, you can ask any England football fan how long ago that was. But since the early recognition that these sediments record changes in Earth's magnetic field, there's been a quest to kind of understand where that fraction's hosted and how it can record some of these changes. Through that, we've learned that magnetic properties and magnetic fraction in marine sediments is ubiquitous, albeit minor, and it generates records like this where we can interrogate changes in the Earth's magnetic field, but it also gives us really high resolution records of environmental change. When we measure these materials, we most frequently do it on bulk sediments. This is a requirement for paleomagnetism, and it also offers that high resolution speed of insight for the environmental change. But what this does is it aggregates all of those different sedimentary processes and averages them into a single value or a single set of values or a single measurement. And this kind of belies some of the complexities that we see with sedimentary records and kind of puts all of those measurements and processes all into that single same value. When actually, sedimentology is one of the main drivers that drives most of our downcore change. And a lot of times, we use magnetic properties indirectly to try and interrogate some of these changes in sedimentology. So what we generally do is we assume some relationship, like magnetic grain size might scale with physical grain size, so we can use a magnetic grain size proxy to track sedimentology, or we can correlate it to some other variable and try and learn what the magnetic record is sensitive to that way. And then we take that record and we go and make some inferences about it. So is it tracking IRD, ice rafted debris? Is it tracking sediment provenance? Is it related to changing current strength? And this can really help guide us how to interpret these records, but it actually does very little to reveal how the magnetic properties or how the magnetic fraction in those sediments are actually hosted. I've got an example up here of a sediment record off the south end of Greenland. And you've got the susceptibility record in red. You've got the magnetic grain size proxy, in this case, Km over K in green. And at the top, you've got an oxygen isotope record, and what you'll see is when you get those higher values, those warmer periods, we see an increase in the susceptibility, an increase in the magnetic grain size. This same record was interpreted two different ways, right? We don't really have an understanding of why it was changing, but through correlation or through inference about other processes, the record at the top interpreted it as during these warm periods, you get increased melting of the Greenland ice sheet, and you get that influx of Greenlandic material, and that drives this coarsening and increase in susceptibility. And then this other record from Eric Drift sediments interpreted that same change in record as you have an increase in the bottom current strength, and that transports a coarser magnetic fraction to the site, and that's what drives some of these changes. So we have this correlation, we have this idea about what's driving these variables, but without the influence of sedimentology, we don't really understand the processes driving some of these changes. So I'll argue, though, some of this for this session, the grand challenge is to really more directly bring in what we should be doing as a community is more directly bringing in sedimentology into our environmental magnetic interpretations to circumvent having to make some of these assumptions. And there's a couple of ways of doing this, right? So we hypothesize, right, that bulk magnetic properties are the sum of many different parts that may arrive at a core location. Am I okay?
Seeing there's a way to make that go away.
Right, I'll let you play with it, Joe. That's probably the worst idea, letting Joe play with the technology, but. So these might arrive at a single location through either diverse pathways or even at different times, right? And there's a couple of different ways that get in at this, right? We've all known about mathematical and mixing techniques, and these are really, really good, right? They're really adept at identifying the presence of different magnetic components within the bulk sediment. That relies on the fact, though, that those components have expressions that you can extract from the bulk sediment value. But again, through this point I'm making, they also have some difficulty, unless you're going to measure it independently, in directly accounting for changes in sedimentology as you're making your environmental magnetic interpretations. So some of the data I'm going to show today, some of our attempts that we've been working on to try and bring in sedimentology a little bit more kind of into this equation. And the way that we go about it is by splitting the bulk sediment down into a range of different grain size fractions, making the magnetic measurements on those fractions, and then trying to understand how in combination you can put them back together to understand what's driving the bulk magnetic property variability. And this can give us some key insights, right? It can tell us, how heterogeneous or how homogeneous are magnetic properties within that bulk sediment. Do they vary with different sediment grain sizes? It can tell us where the magnetic concentration is hosted. Is it associated with a specific grain size fraction? And it can tell us, because we're making those splits and we got the abundance weight percent of those different sediment textures, we can start to independently look at how the magnetic properties are changing, but also how the sedimentology is changing at the same time. So we're going to try and use this approach and show some of the data we've been working on to try and get at, this age-old question. I was talking to Ron earlier, and he said, well, that's a loaded question, trying to get at what are bulk sediments, right? I've been trying to do this for 40, 50 years. I'm not going to solve it in this talk, obviously, but just to try and give you some insights about, how we've been trying to approach this idea. So what we're going to do, instead of just looking at one core, we wanted to look at, more of a basin scale. So we looked at 5 different sediment cores spread across the northern North Atlantic. 2 cores at the top on the continental shelves of Greenland and Iceland. 2 cores on the Erik Ridge, which is a sediment drift, a chondrite drift south of Greenland. And then this record down at Orphan Knoll. So these are integrating different processes, different time periods, so to try and see what the commonalities are and what the differences are between some of these records. We took 362 bulk samples across those 5 records, and then we split them down into 5 different grain size fractions, right? So we did a sand fraction, greater than 63. We did that by sieving. Coarse silt, again, by sieving, greater than 32. Medium silt, fine silt, and a clay size fraction. We split those out by time settling and selling columns. You can see, even just by splitting, this is one sample, right? So this is the bulk sample broken down into different grain size fractions. You can already see there are a difference in color, right? So you can already start to get your head around that, there is some mineralogical fractionation and separation with these different grain size fractions. We dry them, we weigh them, so we know the proportion of the different sediments in the bulk sediment. And then we ended up, right? 362 samples very quickly turns into a lot of data points. So we measured hysteresis loops on all 2,172 samples that we split from this. We did hysteresis backfield curves, susceptibility. So that's why I needed to give a thanks to a lot of the graduate students that worked on this. And then we did forks on a subset of these samples. And we focused initially for this talk, for this, this work, just on doing some of these more simple techniques, the ones that we could do fast to kind of characterize this variability. But with it in mind, that these are the types of techniques that we typically use in paleoceanographic studies to try and characterize some of this rock magnetic variability. Okay, so jumping into some data. This is sediment grain size distribution. So no magnetic data yet, just looking at what is the sediment texture? Like, what is the average sediment texture in some of these cores? The 3 cores on the right are the deep water sediment cores. You can see that clay is really important in these. They're clay-dominated systems, up to 60, or sometimes more than 60% clay in some of these samples. So that's the dominant grain size in a lot of these. Then you can see it drops off. As you get coarser, you get less and less of those fractions. The 2 cores on the left are situated on the continental shelves. So you can imagine close to the land, they've got this greater influx, greater concentration of silt. So it's variable, but a lot of the time we're looking at these systems that are really dominated by clay size fractions. when we look at the susceptibility results, we see a switch in that, right? We see that the magnetic susceptibility is dominantly carried in the fine silt and the medium silt size fractions. So you're looking at those green bars and those blue bars. You're seeing the susceptibility of those separated size fractions, sometimes 5 times, sometimes up to an order of magnitude. Whoa. Up to an order of magnitude greater than the clay size fraction. So clays are texturally dominant, but they really have low magnetic concentration. So the majority of the material is made up with these fine clays, but the magnetic fraction is carried somewhere else, right? And then, importantly, this will be a theme as we go through, you start to see that the bulk values kind of just sit in the middle, like these kind of intermediate values that look like kind of averages of everything that's in the sample. And when you put these back together, you can start to understand, all right, how much of each of these fractions contributing to driving the bulk susceptibility. So what you're looking at now is the contribution of each fraction to the bulk susceptibility value. And you see that because clay is texturally dominant, it does impart, quite a little bit of the contribution to susceptibility, but it's really driven by the contribution of these fine silts and these medium silts. At 1305, for example, medium silts constitute about 1/3 of the sample by its abundance, but it controls almost 3/4 of the susceptibility value. So really, to understand what's driving these systems in this core, we really need to look at what's going on driving that change in the fine and the medium silt. Now for some kind of more scary diagrams, I guess. So this is just, day plots. We've got the 5 different cores. 1305 just blown up so you can see the change in one of them, but so I'm going to make the same changes in every day plot at the same time. And you can see there's some spatial variability. Some of these cores plot in different regions. They all kind of plot in that PSD type box that we're all familiar with. Yeah, so there's kind of some range between different things, but as we start to break these out into the different grain size fractions, so one point I'm going to make now is every single fraction that you see come on now is in that bulk sediment, right? So these are direct measurements of the different grain size fractions in that bulk sediment. If we look at the clays are very different. They plot much higher on a day plot. They've got this concentration of finer magnetic grains. They very rarely overlap, if at all, with any of the bulk sediment data. So they're significantly different to what we're looking at in the bulk data. The fine silt size fraction is a little bit coarser if we're going to interpret a day plot as in a granulometric sense. They fall further down on the MRMS axis. And as we step with increasing grain size, we start to see the magnetic properties follow some of these trends that you might expect under a granulometric kind of interpretation. Got the sand size fraction. If we go back to the bulk, you see that the bulk really is this kind of average of all of the different sum of the particles within it. Then you see some variability, right? You look at 1305 here, and there's a much larger spread. If you look at, say, 2269, you get a much smaller spread. So things close to Iceland kind of look very homogeneous across different grain size fractions. The further you get away, even out into the Labrador Sea, things look very different. So source is obviously playing a big part in driving some of this change. We can look at a different plot. Here we've just got coercivity on the x-axis, and then remnants on the y. And this can start to see, right, what's the coercivity, what's the mineralogy of some of these things, but also like how does its concentration change with the different grain size fractions. We've got the bulk samples there kind of plotting centrally in each of these. Your clay size fractions have higher coercivity, low magnetic remnants. Fine silts, high remnants, kind of an intermediate coercivity. Coarse silts, lower coercivity, kind of similarly high remnants. And then the coarse silts and sands drop down here. And one thing you'll notice that kind of like stunned me the first time I put this one together was that the bulk sediments actually have properties that don't reflect any of the grain sizes themselves, right? So we're measuring something here, we're making all of our interpretation on something that actually isn't reflective of any of the constituent parts that's in that sample. Okay, so we wanted to look at how this affects not just hysteresis properties, but how it affects some of these fork diagrams as well. This is the bulk fork diagram for 2 samples. If I was to present this to anybody in this room, they'd say, well, there's a probably a detrital vortex component there, and there's probably a central ridge, mixture of two components that you might be able to interpret from this fork diagram. If you look at the clay size fraction, we see that central ridge component really strongly expressed in the clay size fraction. We even pick up this negative region, so we're really concentrating our single domain component within the clay size fraction. This negative component isn't being resolved at all in the bulk fork diagram. We do get the central ridge, but none of that negative region. Fine silts and medium silts, these have that higher concentration of magnetic minerals. Unsurprisingly, the bulk fork diagrams kind of mimic what those two fractions look like. And if you remember, the coarse silts and the sands have much lower concentration, and we start to isolate some much more of these multi-domain components. Again, you don't see any kind of signature of those multi-domain components in the bulk fork diagram. So we did some fork PCA to try and tease this out a little bit more. We did 11 bulk sediments, so that was 55 grain size fractions for a total of 66 fork diagrams. We put them into the fork PCA. Two principal components explain about 86% of the variability. Clays have this low PC1 value, and the fine silts and medium silts are discriminable by their PC2 values. We can put the clays and coarse silts on there, but they only contribute a minor amount towards these samples. And then we can look at what the mixing space looks like. And these look very much like, if you went back to the original diagrams, they look very much like the original diagrams, tell us that what we're seeing is this kind of spread across the y-axis in PC1 space, and then kind of movement in coercivity back along the coercivity axis between PC2. So you plot the bulk samples on there, they occupy this really narrow region, kind of between the fine and medium silts. So if you're just to measure the magnetic properties of the bulk sediment size fraction, again, you're looking at that average change rather than the full variability. This isn't something new. Nono pointed this out in his paper like 10 years ago now, that if you really want to understand this mixing space to its full extent, using this kind of granulometric approach is really important to really expand the edges of that data set. So what are bulk sediment magnetic properties? We'll make the argument that they're kind of averages of the properties of all of these different size fractions, weighted by the abundance of those fractions, but also weighted by the magnetic mineral content of those fractions. When you put them together as bulk properties, they really are this muted representation of those individual fractions. And surprisingly to us, when we put this together, we found these fork-based approaches are not entirely free from some of these effects of bulk sample averaging either. And the fine and the medium silts are going to be important to try and interpret some of these. So this raises some interesting questions for the community, right? So do they have physical meaning is kind of the most provocative kind of one to ask. But as we think practically, might sole reliance on them have unintended consequences for how we're interpreting, how we're understanding our records. We put a lot of focus on the clay size fraction for understanding paleomagnetic acquisition, right? And people think that the clay size fraction is important in moving these materials, flocculation to the bottom of the ocean. We're finding that, that might be true, but a lot of the magnetic mineral concentration is carried in these coarser silt size fractions. So maybe we should shift our focus and attention to where the magnetic mineral fraction is carried rather than some of the processes that might bring it down there. But this also provides us some with opportunities, right? So thinking about the talks we had this morning, try to identify where do we find these magnetosomes in sediments. They can be a really small proportion of the sediment. But if we could use, just a granulometric approach to kind of isolate the clay size fraction, maybe that's concentrating where your bacterial magnetite and your single domain magnetite, where your orthogenic minerals might end up in that fraction. So you can start to interrogate, just a grain size split as a first pass. We can start to amplify signatures that we don't see in the bulk sediments. So we can start to look at what might be driving changes in the sands and the coarse silts of the ocean. Probably related to ice rafted debris, we can isolate the signature independent of other processes occurring. Or we can target specific signatures. So there's been some exciting work being done down in the Southern Ocean where people have been looking at people have been looking at, if you want to understand the modal grain size of dust and dust as its transport from Patagonia to Antarctica, why don't you just zoom in and sieve on the modal grain size of dust and try and understand the magnetic properties of that dust, and then relate that to the changes you're seeing in the Antarctic ice cores. So I'll try and quickly wrap up in a few slides saying, okay, they're complicated. There's some results to say we don't really understand what they mean. We have some insights. But at least in the North Atlantic context, what do they mean? How should we use these as a first order interpretation? The Northern North Atlantic experiences a dynamic sediment source and sediment transport regime that's highly variable and dynamic over spatial and temporal timescales. We see erosion of different source materials. Paleogene volcanics are really important. Iceland and East Greenland. Glacial erosion of Greenland over glacial timescales is really important, delivering material into the central North Atlantic. And then the Laurentide ice sheet, when it covered much of northern Canada, is really important for delivering material, again, over glacial timescales into the Labrador Sea. So we can start to split some of these out, and this is some work we did in 2017. We collected actual physical terrestrial samples from these two locations. We split them out into the silt size fraction, and they really nicely discriminate themselves, at least on a day plot, especially in MRMS space. And the reason for that, this is a silt size fraction. So how do you get this grain size variability in the silt size fraction? Well, the reason is that there's two processes going on. One is that Icelandic samples are hosted as really fine-grained inclusions. So they give you that fine magnetic grain size signature within a coarser silt size fraction. And they also have higher titanium content, right? So we've got these titanomagnetites from Iceland. The titanomagnetite concentration will pull you up on this axis. The finer grain sizes will pull you up on this axis. So we look at the silt size fraction, we're looking at that contrast of fine-grained included titanomagnetite, contrasting the more discrete sized magnetites that we see coming out of Greenland. So these sediment records are sensitive to changes in sediment provenance. But these sediments, once they get into the ocean, they're transported along a kind of a vigorous overturning circulation driven by North Atlantic deep water, the strength of which is climatically mediated over decadal to centennial timescales, to millennial timescales. But as we've shown, this strong variability in magnetic properties with sediment grain size means that as the strength of that current changes, that could also impart variability on the bulk sediment record. If you deliver more silt versus more clay, you're going to coarsen your magnetic grain size record. You're going to increase the susceptibility of it. So you can have no change in source, just texture. Can also change how your bulk sediment record is changing. So we need a way to be able to tease these two apart. We hypothesize that if we can subdue some of that variation driven by sediment texture, then we can amplify some of those signatures related to sediment source. And from our terrestrial work, we predict that the silt size fractions are going to be better equipped for us to be able to do that, and that bulk sediments are going to be, sensitive to some of the processes driving change in those silt size fractions. So not to show you everything, but just to show you three sediment cores this time. One dominated by Iceland, one on the Erik Ridge, which integrates Greenland and Iceland material, and then this one in the southern Labrador Sea, which is more sensitive to Laurentide ice sheet instability. So there's our bulk sediments. Our clays all plot on top of each other. We can't really discriminate between the clays. They're really important in the sediment texture, but they're low concentration and they're kind of homogeneity. We can't really tell much about source with them. The fine silts start to move down. We start to see greater separation of these three different sources. We get to medium silts, and we can really start to delineate how these separate out and kind of fall out, at least in day plot space. And then the coarse silts and the sands show, similar variability to what we see in the medium silts. The lower remnants values mean they're not contributing as much towards the bulk values. So really, when we're looking at this as a provenance tracer, the clay isn't great at discriminating those different sources. Fine silt starts to get there. It exhibits some discrimination that would be consistent with source variability. But by the time we get to the medium silt size fraction, we can really start to tease a lot of these different signatures of different source contributions apart in these 3 sediment cores. So then you go to different places and you get different signals, and you get different processes are important, I should say, in different locations. So if we go proximal to Iceland, I mentioned earlier, you see the clay size fraction being a little bit different, but once you get to the fine silts, medium silts, coarse silts, sands, the magnetic grain size, or at least the MRMS values, don't really change that much between different grain size fractions. That's driven by those inclusions within each silt size fraction that just look very similar magnetically. But you do see this variability in concentration, right, in susceptibility. So you see the fine silts and the medium silts are really important for hosting the fraction, but magnetic grain size proxies don't really tell you much, or can't really discriminate, I should say, between the different grain size fractions. Now this becomes really important because sediments around Iceland have been used for a long time to try and interrogate overflow changes in deep water. And people have used susceptibility and correlated them to Greenland ice cores, and they've showed really nice relationships. Some of our data here suggests that that might be actually pretty true and pretty correct. As you have stronger overturning circulation, you have preferential deposition and retention of the silts. Clays might be moved on somewhere else. You'd have coarsening of your physical grain size profile. That would be reflected in the susceptibility results. But people have also used magnetic grain size variability, right, to do the same thing. The idea being that at physical grain size and magnetic grain size scale, you can use magnetic grain size proxies to track overflowing circulation again. And the changes here are much more subtle, right? So maybe the best way to interpret some of these records is for susceptibility. It might be tracking sediment texture under the original assumption of what we wanted it to do. But grain size variations might be tracking source contributions either as well as that might be driven by the same process, or could be totally independent and driven by some other process entirely. So going back to this, I posed this question at the beginning: how do we interpret some of these records? Just going back to the Eric Drift sediments now, you see these changes, these increases in susceptibility, increases in magnetic grain size when we see these warming events, or going from full glacial conditions to interglacial conditions. We see increases in susceptibility, increases in grain size. And again, these 2 different interpretations of the same thing. When we took these apart, we found that the susceptibility in this sediment core is slightly different. It's very close to some of the ones we were working on. Same regime though. We see the same story. The silts are enriched in magnetic minerals relative to the clays. So if we look at just the silt abundance now, we can bring in that texture data, and when we see increases in the silt weight percent, we see increases in the susceptibility. So we can interpret our susceptibility as a proxy for increased silt delivery to this location. And then we can do the same thing with the magnetic grain size records. So this is silt magnetic grain size now, and we can see how that changes. It kind of mimics the bulk susceptibility record. And if we put those M members of source on there now, what we see during these glacial terminations and interglacials, we see an increase in the amount of silt, an increase in the amount of silt coming from Greenland. So we interpret that as related to the warming and the retreat and collapse of the Greenland ice sheet that then delivers all of this silt-sized glacial flour out into the ocean and gives high susceptibility and these magnetic signatures of coarser delivery of magnetite to the location. This was just done on the total silt size fraction. We published this in 2016. Yep. But now we can interrogate this 1305 record with the same kind of variability. So there's the bulk susceptibility record. We're actually going back 150,000 years now. We're looking at those changes. That's the interglacial up there, and we have coarser material, fine in the middle, and coarse on the other ends. We have 2 melting episodes of Greenland contained within this record. If we look at the clay, fine silt, medium silt size fractions, they track what the bulk's doing, right? The clay's a bit more muted. We don't have that discrimination that's afforded as well with the clay. But the bulk really is tracking what's going on in the source of the fine and the medium silt size fraction. If we look at the coarser fractions, they tell us something totally different, right? They tell us that when The bulk record and the fine silt fractions go more Greenlandic-like. The coarser size fractions really go more Icelandic-like. These go more Greenlandic-like, right? So they're tracking some totally different process. We interpret this as two processes going on within the bulk sediment at the same time, right? The fine fraction is really sensitive to deep water sediment transport and the waxing and waning of the Greenland ice sheet. And this coarse fraction is really tracking IRD provenance. So we can, within the same bulk record, we can figure out what's going on at the bottom of the ocean, but also what processes are controlling sediment delivery from the top of the ocean at the same time. Don't worry, Joe, you're standing up. I'm just getting to my key insights. So what did we learn from doing all of these splits? Well, one thing that's not just restricted to these 5 sediment cores, but pretty much every separation I've done on any material, is that magnetic properties really vary strongly with sediment particle size. The bulk sediments kind of just average and aggregate all of that variability, kind of collapse it inward on most of the plots that we put this data on. Clay is important, but it has low concentration and it's largely uniform. So in our context, not in every context, in these North Atlantic sediments, it's kind of an inert component. Fine and medium salts are really important. And then some of the most surprising things, forks and higher order analyses are not entirely free from some of these effects. By isolating specific grain size ranges, we can either amplify signatures that are important for driving the bulk signal, or we can identify and amplify signatures that are actually not even present in those bulk magnetic properties. And that by bringing sedimentology into some of these interpretations, we can identify not only how and where the magnetic fraction is hosted, but we can use some of those observations to really interrogate what are the important processes driving these changes and how should we think about how paleomagnetic records are constructed and how do the environmental records kind of change down core. So our bulk property is a provocative question, right? No, we think that bulk properties are always going to be really, really valuable to everything we do. Some of the arguments we're making here are kind of complementary approaches to try and get a look under the hood a little bit to try and see what's driving them in the first place. And by doing that, we hope we can kind of sidestep some of the assumptions that we normally have to make, right? We normally make some assumption to be able to interpret our bulk record. Hopefully now we can try to look and try and directly observe what's driving those changes from a sedimentology perspective. And then, we can use some of those interpretations that we know about sedimentology. For example, ice rafted debris is going to be concentrated in the sand size fraction. We can isolate the sand size fraction to understand some of those different processes and/or changes. Thank you, Joe.